Right. Church's problem on words that can be solved by an algorithm can be solved by a Turing machine. So if we can do some sort of decision with an algorithm, or we can write out an algorithm which solves some decision problem and returns true or false, then we can do it by a Turing machine. Um, okay, so another version of functions is if we map sigma star to sigma star. In this case, the Turing machine must start with the word W on an otherwise blank. The head is to the left of the word. At the end of execution, the machine must stop with the word f of w on an otherwise blank tape. The head is to the left of the word. So if we have something like this where we have spaces and then we have the start of a word and then we have some spaces. So if we start a Turing machine on that A, the leftmost character, then if there's such a machine which will stop with f of w on another blank tape. So if this will then lead to something like A, B, 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 A, B, okay, doesn't matter where this stops, then this is computable. We can compute the function which maps these words to these words. So thinking of a more sort of relatable example, if we have something like, okay, let me think, Fibonacci. If we want to work out the fib value of some value n, we can write a Turing machine which takes this input and then it returns a word of numbers as an output. So say our input is 3. This Turing machine will take in that input. We can define it with a bunch of states, all of their input and tape alphabets. And this will return an output of, what's the third Fibonacci number? 1 plus 1, 2 plus 1. No, it's just 2, right? 112. Yeah, 112. Yeah, cool. Right, yeah. So we take an input of 3 and then we output 2. So the idea is this is a computable function because there exists a Turing machine which takes in this input and returns this output. Okay. Church's thesis for function states any function on words that can be computed by an algorithm can be computed by a Turing machine. And we can encode anything as a word. So natural numbers, integers, lists of words. We can encode all of this as a word, even an array. And so we can talk about undecidable problems or properties or subsets or languages. Reason being, we can just encode everything as words. But the idea is, despite all of whatever we might call it, Church's thesis just states that if we can solve something related to this sort of encoded data with an algorithm, or solve it algorithmically, then we can also solve it using a Turing machine. Does that make sense? Does Church's thesis? It's not too bad. I think with Church's thesis, it's just about remembering the definition for it, really. And in terms of the kinds of questions that might come up regarding Church's thesis, I think the most we'll be asked is if we're given an algorithm, or we're given something which we know we can't solve with a Turing machine, then we might be asked, oh, can we solve this in Java? I think in the 2023 paper, something like that came up. Let me just find that example question. Because that's the one I just did. And I think, yeah, Church's thesis was in the mark scheme for that paper. Okay, so this was the question from the 2023 paper, and that was the answer. So, mainly part II focuses on Church's thesis. So, a team of TAs for the OOP module have to mark 500 students' sorting programs. They want to write an automated marking software that gives full marks. Can the TAs do this in Java? So, this is a semantic property because it regards the inputs and outputs of the program. And we only care about whether the program sorts it correctly or not. And so by Rice's theorem, sorting programs, like the property of being a sorting program is undecidable. Without running the program, we can't say for sure whether that program will correctly or incorrectly sort that list. But part II, can they do this in a different language? Explain your answer. So this is where you'd sort of bring Church's thesis in. So there's no algorithm in any language that can take a program and return true if it's a sorting program and false otherwise. Because we cannot solve it algorithmically, because we know it's undecidable, we can't solve it algorithmically, then it can't be solved by a Turing machine, it can't be solved by any of the Turing complete programming languages. We can't actually solve it because there's no known algorithm we can use to solve that. So if it cannot be solved by a Turing machine, by Church's thesis, it cannot be coded by Java. Yeah, Exactly. So if there's no algorithm, there's no Turing machine, and vice versa. Cool. That's Church's thesis.